Hi everybody, today I'm going to show you a trick for using the periodic table to help you write your electron configurations. Once you know how to use this trick, you won't have to use an orbital diagram anymore. The periodic table is going to help us see how the orbitals are organized. So real quick, we're going to be chunking our periodic table into some sections like this. And they're going to correspond to energy levels, they're going to correspond to the type of orbital, and they're going to be able to tell us about how many electrons are in there. The blocks that we're going to see on the periodic table are going to end up matching our orbital diagram order. So once you can see the patterns, you won't need that diagram anymore. It does take a lot of practice. You do need to get used to the pattern and the repetition, but once you do, it will be nice to be able to just look at the periodic table and be able to figure out the configuration. One quick thing, the normal periodic table that we look at has this section down here. We call this the F block, and I'll explain why in a little bit, okay? But technically, it's supposed to be inside the normal periodic table. It's just that if we put it back where it belongs, do you see how long the periodic table gets? It would not fit on a normal piece of paper very well. The elements in this F block are very rarely used. They're actually called the rare earth elements. And so because they're very rare, we don't use them a lot. We kind of just chop them out and put this section down at the bottom. That way we're able to fit our periodic table on a normal piece of paper. The problem is, for our pattern to work, we need to understand that it really should be back inside here, okay? We're going to be reading from left to right, and we can't forget that the F block is here. If you use a normal periodic table and you went left to right, you may forget about the F block entirely. So one of the things we'll practice is remembering that it is in fact part of the table. Okay. So next we're going to set up our periodic table. We're going to label it. We're going to take some notes on it. You should have a printed copy. I'm going to be doing this under my document camera, so let me drag that onto the screen. All right. Let me see if I can zoom in at all. Okay. I am going to have to kind of move it back and forth a little bit. It doesn't quite fit perfectly, but it'll be good enough for what we're trying to do. Okay? So I've made a new version of this where I wrote in some boxes and some lines just to try to make things a little bit faster for people. If you don't have this new version, that's okay. You might just need to draw the boxes and things in yourself. Okay? All right. So first, let's think about what we need to be able to find on this periodic table. If we have a configuration, let's just use 2p5 as an example. There are 3 parts to this. We have the big number in front. We have the small lowercase letter. And then we have the superscript that's up top. The big number in front tells us the energy level. The lowercase letter tells us the orbital type or shape. And then the third part, the superscript up here, is the number of electrons in the orbital set. So our pattern on our periodic table is going to have to help us find all three of these pieces of information. Let's start with the energy level because that's the easiest. I'm going to take a marker. I'm going to use purple. You can use whatever color you want. And I'm going to number this 1. This is 2, 3, 4, 5, 6, 7. And if you remember correctly, there were 7 potential energy levels in our atoms. So we can use the rows to help us count energy levels. Okay? Now on this side, we're going to do one thing that's a little strange. We're going to just carefully draw a couple lines through helium. Just scratch it out a little bit. Don't scribble it all the way. Just scratch it out a little bit. And then let's redraw it over here. Helium is a little bit tricky because it behaves like the elements in this column. It's what we call a noble gas. It has a very stable arrangement of electrons, but the pattern works better if it moves over here. It's not a big deal. Remember, the periodic table is just one person's way of organizing the information. There's lots of versions of the periodic table. Some of them are 3-dimensional, some of them look like a spiral, some of them are shaped like a flower. There's all sorts of crazy periodic tables out there. So I'm allowed to organize this in whatever way is convenient for me. And to learn this trick, it's convenient to put helium over here. Okay? So now if we go across, there's no more row 1. So this is still row 2. 3, 4, 5, 6, 7. Now, if you remember, the d orbitals are so strange and they take up so much space that the energy level 1 is too small for any d orbitals. Energy level 2 is too small. Okay? The first time we can have a d orbital is when we get to energy level 3. And if you remember from the slide I just showed you, we're going to kind of chunk these by types of orbitals. So this is not going to be row 4. This is going to be row 3, 4, 5, and 6. And that's going to match the d orbitals that we can have on our diagram. Remember that the F block is supposed to be in here. So this is actually going to be 4 and 5. So now we've found a way to label all of the energy levels. Okay, next we're going to chunk our periodic table like you saw on the slide earlier by orbital type. I'm going to color code these. So I'm using red, and I'm going to outline these 2 columns. And this is going to be called S block. Okay? Next, I'm going to pick a new color. I'm going to pick orange. I'm going to come over here and I'm going to highlight this chunk of elements. And I'm going to call this one P block. Next, I'm going to pick a new color. I'm going to pick green. I'm going to highlight this center part. And this is going to be D block. You can probably guess what the one at the bottom is. Remember, this is the one that we chopped out. using blue, and this is F block. So you can see that we have sections on here that are going to be placeholders for representing the different blocks, the different orbital types that we can have. Next is the hard part. How many electrons are in the orbital set? So off to the side, let's just take a little bit of notes for a minute. The number of orbitals in a set and the number of electrons in the set. So we have S, P, D, and F orbitals. Inside an energy level, I'm allowed to fit up to 1 S orbital. I could also fit 3 P orbitals. I could fit 5 D orbitals. And if it's big enough, right, I can fit 7 F orbitals. Each orbital can hold 2 electrons. Maximum. Okay, really, really important. So if I have 1 S orbital and it can hold 2 electrons, that means altogether in that set I can hold 2. If I have 3 orbitals that are P-shaped and they each hold 2 electrons, that means I can fit 6 electrons in that set. D comes in a set of 5. They each hold 2. So that's a total of 10. F comes in a set of 7. They each hold 2. So a total of 14. Now let's look at something. Look how many columns I have in the S block. I have 2 columns, and I can fit 2 electrons. Look at the P block. 1, 2, 3, 4, 5, 6 columns. Well, that's kind of convenient because I can have 6 electrons. D block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And can hold a total of 10. So how many do you think are in F block? There are 14 columns down in F block. So what we're going to be able to do is, instead of putting arrows into our diagram, we're going to just use the boxes, and we're going to count how many boxes we have to get to. And each box is going to be a placeholder for one of our electrons. Just like on our orbital diagram, we were putting electrons into the boxes as placeholders, we're doing the same thing here. Okay. All right. Next thing I'd like to do is just kind of highlight the fact that after barium and radium, you got to come down here to the F block. Once you're gone through the F block, at the end, you got to go back to the D block. So just trying to remind people with our highlighter that that should really be inside. If I read left to right, I'm going to read this way, then I'm going to come down and read across, and I'm going to loop back up here, okay? You may notice that not all periodic tables are set up quite the same. Sometimes they put lanthanum and actinium in slightly different places, or they may put lutetium and lawrencium in slightly different places. It's not a big deal. I'm never going to ask you to do a configuration for something that breaks a rule or that might be tricky. So don't worry too much about that. Okay. All right. I think we are basically set up so that now we can learn the trick. See this big star up here? That's because we're always going to start up at the top corner. Remember, our configurations always start at energy level 1, and we start putting things into the s orbital first. So we always are going to start up here. We're going to list the energy level, the block, the orbital type, and then we're going to list how many boxes we had to go through before we got to the element that we were interested in. Okay? So for example, if you look at oxygen, oxygen has 8 electrons. Well, if you count, there's 1, 2, 3, 4, 5, 6, 7, 8 boxes. So each box will basically be a way for me to count out my electrons. Okay? I'm going to start with hydrogen, and then I'm going to do helium, and then I'm going to do lithium, and then I'm going to do beryllium, and then I'm going to do boron. I'm just going to keep going in numerical order. Okay? Pretty soon, you're going to notice the pattern that I'm doing. When you notice it, I would like you to join along out loud, even if it feels silly and sounds silly to sit in your room and you're just talking to yourself like that. You know, I do think that there is a lot of benefit to hearing it out loud. Saying it helps our brain internalize the pattern, and it really helps us memorize it. Okay? So, let's start with hydrogen. 1s1. I only had to go through one box to get there. Helium. 1s2. I had to go through 2 boxes to get there. Lithium. 1s2. 2s1. Beryllium. 1s2. 2s2. Boron. 1s2. 2s2. Go all the way across. I'm still in energy level 2, but now I'm in the P block, so my counting starts over. Okay, so let's start at the beginning again. 1s2, 2s2, 2p1. I only went through one box in the P block, so that's why it ends like that. Let's do carbon. 1s2, 2s2, 2p2. Nitrogen. 1s2, 2s2, 2p3. Oxygen. 1s2, 2s2, 2p4. Let's skip to neon. 1s2, 2s2, 2p6. Now that those p orbitals are full, if I go any further, I have to go to a new energy level and to a new block. Okay? Let's do sodium. 1s2, 2s2, 2p6, 3s1. Magnesium. 1s2, 2s2, 2p6, 3s2. Let's skip all the way to chlorine. 1s2, 2s2, 2p6, 3s2, 3p5. All right, let's do another one. Let's do scandium, number 21. Okay. Start at the top. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. The reason why we don't fill the d orbitals up here when we're doing the rest of third level is because the d orbitals are such strange shapes. They put the electrons a little too close together, so they don't really like it. It's not as stable. It takes too much energy. So it's kind of postponing. It doesn't want to fill these weird d orbitals until it really, really has to. The joke I always say is I used to postpone my English homework until I really, really had to do it. We'll still fill them eventually, but I'm going to kind of skip ahead and do a little bit of something that's easier before I have to come back and fill these. So they are third energy level in terms of distance from the nucleus. This is really talking about how far away is the orbital, okay? The 3D orbitals take too much energy to fill up here, so they get pushed down in terms of the filling order, okay? Remembering to go from row 4 to row 3 is a huge common mistake people forget. When we come back out of the D block, we go back to row 4, okay? So we have to go down and then back up. We'll do the same thing when we do the F block. If you look, we waited a really long time to fill an F orbital. They're distance-wise level 4 from the nucleus, but they're so complex, we want to wait and fill them until we absolutely have to. So we'll get all the way to 6s, and then you come down, and then it's 4f. Then you'll come back, and it will be 5d. And then you get here, and it will be 6p. Okay? So we're going to have kind of this going down and then coming back up pattern. So let's try copper. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. People sometimes in the D block lose track. If you have to literally count 1, 2, 3, 4, 5, 6, 7, 8, 9, that's totally fine, okay? All right, let's do krypton, number 36. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Okay. Let's do 10. We're going to kind of do one in every row, okay? Let's do 10, number 50. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2. All right. Let's do tungsten, number 74. For the sake of time, let's just pretend like we did everything on the top, and let's just start here, okay? So we'll just pretend that we started all the way up here. So we went through, we did it all, we got down to here, and we say 5s2, 4d10, 5p6, 6s2, careful, 4f14, back up here, 5d4. So if you noticed, we went from 6s to 4f and came back and did 5D, okay? And if you look at your orbital diagram, you would see that same pattern. The 6s boxes are there. Next would be the 4f boxes, and then you would see the 5d boxes, okay? Let's try one that stops in the F block. Let's try samarium. Let's do the same thing. Let's pretend we started up here. We set everything all the way down to here, and we'll just keep going from 5s, okay? 5s2, 4d10, 5p6, 6s2, 4f5, okay? You're not going back to the D block if you haven't finished the F block first, all right? Let's do mercury, number 80. Same thing, we're going to pretend like we said the top part, and we're going to get down to mercury. Okay, ready? 5s2, 4d10, 5p6, 6s2, 4f14, 5d10. Let's do the very, very last one on the entire periodic table. If we can do the very last one, we can do any of them, okay? 118 electrons, and since it's our last one, let's start at the very top and do the whole thing start to finish, okay? Here we go. We're trying to get to here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. Very last one. Okay. Oh, that was a lot. I would like to add just one more thing to this periodic table that can be explained with all these configurations, and that's which ions it likes to make. Okay. Everything in this column likes to lose an electron and become a +1 charge. Everything in this second column likes to make a +2 charge. We're going to skip the D block. We're going to come over here. Everything in this column likes to make a +3 charge. The carbon column is a little weird. It makes a + or -4 charge. Nitrogen's column likes to make a -3. Oxygen's column likes to make a -2. Fluorine's column likes to make a -1. And if helium were here, it would be part of this noble gases, and everything in that column doesn't like to make a charge. These noble gases have what we call a full shell. They are very stable. If the s orbitals and the p orbitals get filled, it's much more stable. Okay? Everything wants to look like a noble gas. Fluorine does not like that it only has 9 electrons. It really wishes it had 10. Okay? Oxygen doesn't like that it had 8. It really, really wishes it had 10. Nitrogen doesn't like that it only has 7. It would really rather have 10. So nitrogen steals 3 electrons from something else so that it will look like neon from the outside. Oxygen steals 2 electrons so that it looks like neon. Fluorine will steal 1 electron so that it looks like neon. Okay? If you look at like phosphorus, actually no, let's look at silicon. If silicon steals 4 electrons to be a -4, it would look like argon. Instead of 14, it would have 18. Or it could lose 4 electrons and it could look like neon. So the reason this carbon column is plus or -4 is because it's equidistant from a noble gas on either side. It could gain 4 or it could lose 4 and look like the previous one. Carbon can either look like neon or it could look like helium. Okay? On this side, look at sodium, which sounds easier. Having to go steal 7 electrons from other atoms to look like argon. Or just getting rid of 1, giving it away to something else so that it now has 10 and looks like neon. Well, just giving rid of 1 is much easier than stealing 7. That's going to help us predict which atoms like to bond with each other. Okay? Sodium and fluorine are a perfect pair, aren't they? Sodium wants to get rid of an electron. Fluorine wants to steal an electron. Perfect match, right? They just trade and they're happy. Sodium gives it to fluorine. Now fluorine's happy. Now sodium's happy because it doesn't have that extra electron. So these charges are going to be very helpful down the road. The D block is a little weird because the D block can make what we call variable charges. And same with F block. Because these orbitals are so strange, they can do a lot of weird stuff. So you could have copper +1 or copper +2 or copper +3 or 4. You can do a lot of different things in here. So they don't always behave the same way. I would give you information about what charge they were making under the circumstance. The ones in the S and P block will follow the rules. You will know that magnesium is a +2 because it's in this second column. You will know that phosphorus is a -3 because it's in this column. Okay? So the S and P block follow the rules much better than the D and F block do. Okay? Let's jot down just a little reminder about our ions. So the ions, remember atoms want to look like noble gases. They want a full shell, meaning they want those S and P orbitals nice and full. Okay? We'll make ions to fill its shell. We have 2 options. We can make cations or we can make anions. A cation has lost electrons. Anions gain electrons. A cation now has more protons than electrons, which means it ends up having a positive charge. Anions gained electrons, so now they have more electrons, which gets us a negative charge. Okay? So from just this periodic table, we can see lots of patterns. We can tell which energy levels are present based on counting the row. We can tell what orbital shapes are being filled by looking at which block we're in. We can figure out how many electrons are in those orbitals by counting how many columns we've gone through. We can figure out the charge that it likes to make based on which column that it's in, all from looking at a periodic table, okay? So it's a lot of information to process. It will take a lot of practice, but that's why, we find practice for you to do. So hopefully that was helpful, and we'll go on and do some practice. We'll get a lot better. Pretty soon you'll be able to do this with a periodic table that isn't even labeled, right? I know how this is labeled so well that I don't even need to look at this anymore. I can just look at a blank one and I'm good. And you'll get to that point too. All right, everybody, bye.